Okay, so we now go to the notes. Okay, AC voltmeters using rectifiers. So like I said, the device is measuring AC, but that AC signal is actually being rectified first. So before the device begins to manipulate it, it rectifies the signal into DC. So it is the DC that the device is working on. It is the DC that is being measured. But you now calibrate the meter as measuring AC. But manipulation has taken place. The AC signal has been converted into DC, amplified, and then you take it to the meter. So if you look at the simple case of that device that we have in this circuit diagram, this is the simple case, figure A here. We have DC mode of operation, whereby you have AC input taken to a diode. You know a diode is a rectifier, isn't it? This is just like a single wave rectification. You now convert it to DC. And that DC is taken to an amplifier. The output of amplifier is now taken to the meter. And that's just a simple way by which it operates. That's the simple way. Now, the other way is to actually amplify the AC input first. The output of the amplifier is now rectified. Before you now take out
Hello, sir.
the meter.
Hello, sir.
Yes?
Yeah, the screen you are sharing is not the note, sir.
It's not the notes?
No, sir, it's not the note, sir.
Okay, I will do it again then. I think you have it now.
Okay, yes, sir.
Yes. Figure A here, we have DC mode of operation that I have explained. I will repeat it. The DC mode of operation is that you bring in the AC to the device. First thing the device does is to convert that DC, this AC to DC by means of this diode. So the diode comes in first as a rectifier to convert the AC input into DC. The DC is now taken to an amplifier and amplified. After amplification, you now convert, you now take the output of the amplifier to the meter. This is the meter. So you now measure DC current on the meter. And that DC current is what you calibrate as if you are measuring AC voltage. Very interesting, isn't it? Very interesting. So that is the mode 1 of operation. That is DC mode of operation. Now we also have AC mode of operation. AC mode of operation is not serious. AC mode of operation is nothing serious. Okay? It's just that the signal comes in. Then, before it is rectified, it's applied to an amplifier. So AC is being amplified first. After amplification, then the output of the amplifier now is taken to a rectifier. You can see 2 diodes here. This is full wave rectification using 2 diodes. So the diodes now convert it to DC. It is after the diode has converted the signal to DC, you now apply it to a meter. The meter now takes the measurements. At the end of the day, AC comes in and then it's being measured as DC. But before then, it has been amplified in form of AC. AC signal has been amplified first before it is taken to the rectifiers, the diodes that serve as rectifier. So that is the AC mode of operation. I think you see the slight difference between the two now. One carries out rectification first, the other one carries out rectification last. Rectification last. So that's the difference between the two. Okay. So the RMS value of the voltage that has equal positive and negative excursion is related to the average value by the form factor. So the form factor is given here. You know, we are dealing with AC measurements. So okay, somebody is still using his mic. Let go. Afolabi, I am muting your device so that I don't kick you out of class. Okay. We go back to the notes. Okay. So the form factor K is ERMS divided by EAV. ERMS divided by average voltage. RMS voltage divided by average voltage gives us the form factor. That is 0.707 of the E peak. That is EM, E maximum, E peak, peak voltage, divided by 0.636 of the E peak, the peak voltage. And the answer is 1.11. So when an average responding voltmeter has a scale marking corresponding to the RMS value of the applied sinusoidal input voltage waveform, those markings are actually corrected by a factor of 1.11 from the true average value of applied voltage. That is, what the meter is going to measure, they are going to use 1.11 to multiply it. What the meter is getting is a little slightly lower than the real AC. As you know, the meter is measuring DC, but what we are applying is actually AC. So there is a slight difference due to the form factor. So to correct it, get the actual value of what is being measured is going to be multiplied by 1.11. That is the way these meters operate. Are you there? Are we there? Are we together? Okay. So I can see you are nodding, Mr. Wayne. I see. Afalabi straight, smiling slightly. I see you. It's okay. I know you are getting it. It's not really difficult. And then the note is even explanatory. By merely looking at the notes and the schematic diagram, you can easily grab what is being said. Okay, now the next one is differential voltmeters. Differential voltmeters. Before I continue, let me ask, you people, I don't know, how many people have turned in the assignment online? Have you submitted the assignment? You have not. You are shaking your head, Mr. Nokia 6.
We are still working on it, sir.
Mr. Suberi, are you the one saying that?
Yes, sir.
I think next week will be the deadline. If you don't meet up the deadline, that is 0. Because you won't be able to submit it on the portal again.
We will meet up, sir.
Let me just inform you about that. If you don't submit, you know, the thing we are putting time there. When you want to upload the assignment, you put time, you know, starting from the day you set and the last day. If you don't submit on that period, the site will not allow you to submit again based on the program. So please submit your assignment. It's important. And then that okay, I think some 2 fellow missed our tests. Who are those people that missed tests here? You are raising up and okay. Mr. Awe and Zubair, 2 of you. Yeah. It's okay. It's okay. Let's continue with the lecture. This man using Lego T5. Mute your mic. Mute your mic. Mute your mic. Let's go back to the lecture. Differential voltmeters. Now, when you hear differential voltmeter, something must come to your mind. Differential. What is it about? Differential is all about difference. The word is actually taken from the word difference. So a differential voltmeter is actually working based on difference, checking the difference. And which one is difference? The principle is such that inside the voltmeter, there is a standard value of voltage that has been kept there. The standard value of voltage is kept there, like 1 volt. Now, that 1 volt is going to be used to compare any voltage you are bringing from outside. Even if it is 15 volts, if it is 100, if it is 150, the device will now compare your incoming voltage to that 1 volt, regular 1 volt that is kept inside it. Meaning that if your own is now larger than the internal voltage, then it's like twice the internal voltage. It means what you are bringing in is 2 volts, isn't it? If the device sees that the voltage you are bringing from outside is about 15.5 larger than the internal voltage, it means what you are bringing in is 15.5 volts. You see the beautiful way that device works. And then because of this method is usually very accurate in taking measurements. Very, very, very accurate because it has a very, precise value inside 1 volt. And it's using that 1 volt to compare every other voltage that is it's being measured by the device. Are you raising up your hand? Israel.
Yes, sir. Sir, I just want to ask something from the DC mode of operation of voltmeter using rectifier, sir. The RFB, what's the RFB? Is it the load or what, sir?
What's what?
The RFB from the circuit diagram here, sir. The RFB.
The thing is this, what that meter is measuring is actually current. Did you notice? So there's need for a resistance to be in that circuit. Otherwise, current will not be drawn. Do you agree? That is why they put that RFB.
Okay, sir.
That RFB is a resistance. It's serving as what is drawing the load.
Okay.
It's a feedback resistor. I think you can see that the thing is taken back through the resistor. But that is what's actually drawing the current to that meter movement before you can measure the current. But the current is being calibrated as voltage because it is a voltmeter we are dealing with. I think that's clear. Okay.
So
we go back to our interesting differential voltmeter. Differential is checking difference. Bear it in mind. It's using a standard voltage that is kept inside it of 1 volt to check what is the value of the voltage you are bringing from outside to be measured. So if you look at the block diagram here, you see the simple block diagram. We have reference section, 2 blocks, 1 volt reference supply, then decimal dividers. Decimal dividers, they are there to convert the 1 volt into decimal values. Okay, then we have amplifying section. The amplifying section now amplify the voltage that you have brought from outside. Then the two of them meet. The voltage you brought from outside is connected through these selectors: 1 volt, 10 volts, 100 volts, 1000 volts. These selectors. So when the voltage gets in, it's amplified in a way, and then it's compared to the reference section. So the device will now know what is the value of the voltage you are bringing in after comparing them. Now see the difference. Okay, the one you are bringing in is larger than the internal voltage, maybe 10 times larger. It means that voltage is 10 volts. So you're now taking that one to the outside, precision DC output. It's measure it from 0 to 1000 volts DC. That's the simple way it works. The only thing is that you need to capture the block diagrams and then be able to explain the few things and label the block diagram correctly. The differential voltmeter requires a reference source to make a measurement and a meter circuit to detect an imbalance between the unknown voltages. The instrument has 3 modes of operation. Basically, DC differential voltmeter and then DC voltmeter. Then we have a function switching that allows many of the same basic circuits to be used in each mode of operation. So the selector here will select the voltage to the same, internal operation. Just by selecting, the voltage is taken to the same place. It's only the range selector that help you to connect to the appropriate range of the voltage you want to measure. The standard mode of operation. Okay. Let me add something to the note. Something is missing. If you check this place, the instrument has 3 modes of operation. Namely, after the word namely, there should be standard. Standard. This is standard mode of operation, and then standard mode. DC differential voltmeter and DC voltmeter. The device can work in that 3 ways. Those 3 ways, rather. Now, the instrument generates precision output voltage from 0 volt to 1000 volts. Then there's a temperature control reference supply that generates a very stable 1 volt DC. Here, if it's in your notes, check this place. The temperature control reference, not referred. If in your notes it's referred, kindly change that, it's reference. the temperature control reference supply that generates a very stable 1 volt DC plus 1 volt DC. It is what that meter uses to generate readings for several other voltages from 0 to 1000. Okay, the voltage is then applied to a decimal divider network. That is 1 volt is applied to decimal divider network. And the output voltage is applied to a high gain DC amplifier with the generated voltage feedback to obtain precisely controlled gain characteristics. All these other ones, they are just stories. The main thing is what we have discussed. The main thing is what I have summarized to you, that the device has a reference voltage, which is actually a very stable reference voltage. That reference voltage, 1 volt, is used to compare whatever voltage is being taken into the device. And with that, the device can tell you the value of what is being measured on the meter output. And here, if you look at what we say, it's a precision DC output, meaning that the device is highly accurate. Highly accurate. Why? Because it's using one standard voltage that is highly stable voltage to compare to any other voltage and check what is the difference between the two of them. So that is it. Now the next one, I don't know whether you have any question before I move on. Any question? If we do it well enough, by the time we have 2 more Zoom meetings, we will finish this course. Are you with me? So God's willing, after like 2 more lectures on this Zoom, we finish this course. Meanwhile, the school management has said that we should start second semester. All our courses for second semester should be started on Zoom with you people. I think I have 2 courses to take you people in second semester. Is it 2 or 1? Research methodology. I think it's 1 now. I think the other one is in third semester, I think. So, but I have research methodology to take. So I need to finish this one before I go to research methodology. I don't know whether other lecturers have contacted you people regarding your Zoom classes for second semester. They have not. Yeah. They will contact you, because when we resume, we won't have plenty time to receive lectures before we write exam. That's what the management is targeting. They want us to do most of the lecture now and come and finalize it maybe in 2 or 3 weeks, then we'll go for exam, because too much time has been spent under lockdown in the year 2020. So let's go back to the note and continue. Okay. So we have digital voltmeters. Digital voltmeters. There are 2 types of digital voltmeters, and those are ramp type DVM and then staircase ramp DVM. Ramp type DVM and staircase ramp DVM. DVM is just an acronym for digital voltmeter. An acronym, DVM, digital voltmeter. So we take a small part today because it's almost 1 hour that we started. Ramp type digital voltmeter. The operating principle of the ramp type DVM is based on measurement of the time it takes for a linear ramp voltage to rise from 0 to the level of the input voltage. What is a ramp? A ramp is actually a voltage that is increasing gradually like a slope, rising from 0, going gradually like a slope, up. That's what is called a ramp voltage. Now, when you have a ramp, it's like when you have 2 axes and then you draw a line from the middle of the origin and then you draw it diagonally up straight. That is the kind of waveform you will get when it's a ramp. That's the waveform you will get. That's what we call ramp. Now, the device measures the voltage by making a comparison between this ramp voltage and your input voltage that you are measuring. It will now look at the time that the ramp voltage rises from 0 to meet up with the input voltage that you are sending. So the time taken is what it uses. You now do a counting, counting the time it takes for the ramp voltage to rise from 0 to the value of the input voltage. So this time is measured by an electronic time interval counter, electronic counter. And then it is displayed as a number of digits on electronic indicating tubes. So in a way, the device converts the voltage being measured into digital readout by means of that. It is measuring time based on electronic counters. The time it will take the voltage to rise up from 0 to the value of the input that is being measured, and it show the value outside, and that will be the value of the voltage that you're actually measuring. So this is the block diagram here. This is the block diagram. That is very interesting block diagram here. You see how nice it is. We have the DC input voltage applied to the ranging and attenuator block. The ranging and attenuator block is connected to an input comparator. Basically, a comparator is an operational amplifier that is used to compare two voltages. Instead of amplifying voltage straight, it's comparing them. It's used to compare voltages. Then, the output of this comparator is applied to a gate, whereby we have oscillator controlling the gate. We have the start and stop pulse at the gate. That gate is counting the pulses that goes to the counter. Before the counter will now bring out the value on the digital readout. So, but before the gate starts, it's going to wait for a pulse from the input comparator. So when it's counting, when the value of the voltage has been reached, then a pulse will be sent from the ground comparator to stop counting. And whatever has been counted on the counter will now be given out on the digital readout as the value of that voltage. So when the input voltage is applied, an oscillator generates clock pulses which are allowed to pass through the gate to a number of a decade counting units, DCUs, which totalize the number of pulses passed through the gate. So the decimal number is displayed by the indicator tube associated with the DCUs, and that is a measure of the magnitude of the input voltage. So the sample rate comparator determines, sample rate multivibrator determines the rates at which the measurement cycles are initiated. Then it provides an initiating pulse for the ramp generator to start its next ramp voltage. So that is what determines when the voltage is going to start next time when you want to take another measurement. Otherwise, the last count could affect the new count, but the multivibrator will now help them to reset so that they start another one. So it also provides an initiating pulse for the ramp generator to start its next ramp voltage. At the same time, a reset pulse is generated. Reset pulse is generated, which returns all DCUs to their zero states. That reset will now remove all the readouts on the digital, readouts from the counter. It resets it so that the last reading will not affect the incoming reading. And that is done by multivibrator. Multivibrator, synchronizes that. The time we have finished counting for these measurements, and then to stop, and then when to start next one. It tells them when to start next time, tells the gate when to start next one, and also it tells the counter to reset, to remove the last reading and set all of the DCUs to 0. The digital counting unit, those are electronic counters, decade counters rather, decade counters. When you say decade, something that counts in tens, from 0 to 9, 0 to 9, 0 to 9. Each one can take a display of 0 to 9. They cannot display anything from 9. It's only 0 to 9. 10, 11, no, they are not displaying in two digits, only one digit, 0 to 9. So they are called decade counters or decade counting units. So they have to be reset to 0 after each measurement so that the last reading will not affect the present reading. And that is taken care of by the multivibrator. The sample rate multivibrator does that work. You can see that the sample rate multivibrator is connected to the ramp generator, which is linked to the input comparator, and also linked to the counting unit, and also linked to the gates. The sample rate multivibrator feeding all of them, that is what is controlling all of them, synchronizing their work together so that they can start at the same time, stop at the same time, reset at the same time. That is what is taking place. So that is the function of this sample weight multivibrator. And that is the simple principle of operation of the digital ramp type digital voltmeter. Ramp type digital voltmeter. The next one will be staircase ramp. Staircase ramp is actually, the word staircase is added because it's also a ramp voltage that goes from zero, rising as a slope to the maximum. But it's not going as a straight line. It's going as if you are climbing your staircase, forming staircase. You know how the staircase look like when you draw it, something like that. If I want to show that on the screen, I draw something like this. I sketch something on the screen for you like this to see what I mean by staircase ramp. Now, if I have ordinary ramp, I can draw ordinary ramp like this. This is like ordinary ramp voltage, a voltage that goes from zero to maximum in a slope, rising gradually up. Now, on the other hand, a staircase ramp is having steps. It's having steps. Something like this. It's also rising up from zero to maximum, but it's not going as a straight line. It's not going like a straight line. I think you see it. Something like this. I think you can see my screen. So if I want to join another one to it, can you see it?
No, sir.
You can't see my screen?
Yeah,
No,
we can't see it, sir.
See the old screen that is there, sir.
Okay, I will show you this one now.
Yeah, the stuff is just.
Let me show them. Yeah, let me show them.
That's not the ramp I'm showing you. Let me show you the ramp from the Zoom directly. I show you from the Zoom now. Zoom is telling us to upgrade to pay $13 so that it will not time out. So that it will not time out again. Anyway, let me show you what I'm showing on the drawing on the paint. You see this straight line now?
Okay.
The straight line is ramp voltage, starting from zero, going to the maximum as a slope. But the staircase ramp is also going from zero to the maximum, but it's not going like a straight line. It's forming steps. So that's why they call it staircase ramp. It's moving gradually from zero like a slope, but doesn't go like a straight line. It forms steps, 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 steps until it goes to the maximum. So that is how the staircase ramp is. I think you see it now. So that is ramp voltage. The straight line there is ramp voltage, and the other one, zigzag, is the staircase ramp. Okay. Okay. So after the staircase ramp, we will stop today. So the block diagram of the staircase ramp is the next one we are going to show. Then the DVM, the staircase ramp DVM, makes voltage measurement by comparing the input voltage to an internally generated staircase ramp voltage. That's a staircase ramp voltage inside is generated, and then you move it up like that. So when you take a measurement from outside, the digital device, the staircase ramp DVM, you now compare the ramp inside, the voltage inside it, to the one you are measuring from outside. So the measurement cycle is first initiated by a clock, which is something 1.5 kilohertz realization oscillator that produces pulses to 3 DCUs in cascade. The DCU are decade counting units, and the unit counter provides a carry pulse to the 10 decades at every 10th input pulse. 10 decades can't carry the input pulses from the unit decade and provide its own carry pulse after it has counted 10 carry pulses. This carry pulse is set to the 100 decade, which provides a carry pulse to an overrange circuit, which in turn causes a one panel indicator to light up. warn that the operator that the input capacity of the instrument has been exceeded. What are we talking about here? The device has 3 DCUs. Just like when you are doing 100 tens units in primary school, when units, you are adding 2 numbers under units, and then they are more, the value, the addition, the total is more than 9. It's going to be 10. Then you write only 0 and carry 1 to tens. If you are adding under tens and then the addition is like 11, you write only 1 and carry 1 back to 100. That is what is happening under these DCUs. They carry their measurement over to the next grade. But if the total measurement is exceeding hundreds, then there will be a red light that shows as indicator to tell you that what is being measured has exceeded the limits of the device. So the operator will now switch to the next higher setting on the device. It switches the device to the next higher setting as input selector. It changes the input selector to the next higher setting. So each of these decade counting units is connected to analog to digital converter, which convert the output of the digital digital to analog converter, and then outputs of the digital to analog converter are connected in parallel and provide an output current proportional to the current counts of the DCUs. So the staircase amplifier converts the DA current into a staircase voltage, which is applied to the comparator. When we see the interesting circuit diagram here, you will understand better. Interesting block diagram. I think you see this interesting block diagram. Very nice, isn't it? Very nice block diagram, isn't it? Very simple, Abby. It looks simple. Is it simple?
It's not simple, Oga.
If somebody asks you to
It's not
solve this
simple.
one in an exam,
It's not simple.
again. Anyway, when you go through over and over again, then you see the meaning of those blocks. So for today, this is where I want to stop. This is where I want to stop. The comparator senses the input voltage and the staircase voltage. Then it provides a trigger pulse to stop the oscillator. Once the input voltage has equated to the staircase ramp voltage, the comparator senses a pulse to stop the oscillator. When the oscillator stops, the DCU, digital to analog converter, stops. Then the current value on the DCU are the value that represent the measured voltage at that particular point in time. That's where we are going to stop for today. Then next class, we are going to go to wave analyzer. Wave analyzer. Are we there? Are we there?
Yes, sir.
Yes, sir.
So I don't know whether you have any question. Any question?
Hello, sir.
Yes.
So I think maybe we should look for a kind of way to explain this ramp digital voltage very well.
We should look
there
for
are
what?
some towards the end of, like, to explain it very well. Because towards the end of the explanation, I think I personally got lost.
You will listen to the lecture again in video. I will send you the video, and you have the notes with you.
Okay.
That's why you are in HND.
Okay.
Yeah. The note is explanatory anyway. It's not difficult to understand, isn't it? See how
I don't think so.
Mr. Abatude Awe is looking at me, enjoying my comments. Yes, any other question?
The assignment you gave us.
Yes.
The assignment you gave us.
Yes.
I've been finding it so difficult to look for a very good way to explain it. Not until now, while you were explaining, I think I got it right, and I was jotting exactly what you were saying. I think I have the solution to the assignment for the number 1.
No problem. I gave you 2 weeks. I knew we must have covered it before you actually, do it and do it well. Do it very well and upload. Upload it as PDF to the portal. Don't make mistake of clicking submit without uploading PDF. Because I've seen some students uploading in ND and HND too. They will upload empty PDF. Any empty PDF I see is 2 over 10. I won't score you more than 2. Why some people will get 8 over 10 in that assignment? If I didn't see your PDF, it's 2, only 2. that you made an attempt, but you did not submit. I'll give you only 2. So make sure you submit your PDF. Any
Sir.
other question?
Sir, at the same time, I think last week we were contemplating on are we to type it or to write it through hand? Sir?
Type it as PDF. Save it as PDF.
But sir, unlike the okay, no problem, sir.
Unlike what?
Because in a case whereby an assignment is given, the assignment that involves drawing.
Yes, you should learn how to use computer to draw now. You can draw it.
Sir,
Don't you think you can draw
Hello,
it?
sir.
Anyway, if you can't draw
Hello,
it
sir.
using a phone,
Can't
maybe
we
you don't
just
have
scan
system.
the assignment?
Listen. If you can't draw it using your phone, or you don't have a laptop to draw it on paper, scan it and put it into the PDF, into the right position.
Okay, sir.
You put it in the right position in your Word file.
Right, sir.
Then save that Word file as PDF. That's all. Yes, I allow you to do that.
Okay, sir.
But you should be able to draw with your computer. All this drawing you see in my notes, I drew it personally. I drew it by my system, by myself on the system. All this drawing I've been showing since morning. Every drawing in this note, I drew it myself with computer. It's nothing special. So you should learn how to do the same because it's part of the training. You cannot become a HND graduate that doesn't know how to use computer.
Not that we can't.
Any other question? I want
But
to go.
it's the time.
Yes?
All right, sir. No problem, sir.
I want to go home because night is already falling.
Um,
A mosquito is disturbing me here. Mr. Awe, good night. Should I
Yes,
leave
sir.
the
Good
Zoom
night,
for
sir.
you or I should end it?
Leave it
Okay,
for
can
us, sir.
leave it, sir.
I should leave it for you.
Yes, sir.
It's okay. I will stop recording now.